Hi, it's Miss Molesbury here. This video today we're going to go over properties of logarithms. So we're getting ready to solve logarithmic equations. We're putting everything from our last unit together with a few skills early on in this unit so that we can solve any sort of equation that's exponential or logarithmic. So I want to show you what those properties are, and then our goals today are going to be to expand expressions and condense them as well. So let's jump into it. Just a reminder at the beginning, of course, we can go from form to form. This is saying in our exponential form, we have our base, our exponent, and whatever that equals. If we rewrite that as a log, the base is the same, but the log is equal to the exponent that was needed there. And your teacher may have shown you, of course, the easiest way to rewrite these. Start at your base, kind of loop around, follow that pattern as you go. Base, other side of the equation, and it'll show you what that expression should equal. Common log versus natural log, just to review. Common log has a base of 10, and it'll be written as log of x, or log of whatever value. Our natural log has a base of e, and it's the natural log x. And today you won't actually need a calculator, but these are both the buttons next to the 7 and next to the 4 on the graphing calculator. Okay, some basic log properties that are true here. And I would suggest maybe think through it. Like pause, try to guess and see, do you know what any of these are ahead of time? The log base a of 1 is 0, because think about what a log does. It says, how do I get from this base? What exponent is needed to get to 1? A 0 is needed because a to the 0 power is 1, anything to the 0 power. So then if I want to take the natural log of 1, this is just saying e to what power is 1, so it's also going to be 0. So regardless of the base, any log of 1 is 0. Next column, log base a of a. Well, how would I start with a base and get the same number? The exponent I would need is 1, because this would be a to the first power is a. So then on the next one, when I see natural log in e, remember the implied base here is an e, so to get from the base of e to e, I need the first power. The next one we could think of a couple different ways. So this is like saying, let's see, I'm going to rewrite it. A to some power makes a to the x power. Oh, well, that's just going to leave an x, right? Or you could say, I know that to get from a to a, I would just need 1, and then I would need the x. Or you could see that if I have the same base and argument, they're basically canceling and leaving a 1. We'll talk about a property of log today that makes this a little more clear. And so similarly, if it's the natural log of e to the x, this is saying e to what power makes e to the x? Well, we would just need an x. Okay, so these powers I keep mentioning here, they're related to our exponential properties that we already use. So the product rule for exponents, we know if we have a base to the x power times a base to the y power, when they multiply, the exponents add. Okay, well, similarly, if you see a log and we're taking the log of x, not x plus y, product rule, if you have a log and it's the log of x times y, since a log represents missing exponents, that would come from the log of x plus the log of y. And I could put parentheses here. And y'all, this goes both ways. So if I see the log where the argument is multiplying, I can expand it and add those together instead. It's like these are representing the exponents here. So when you see them multiplying, you can separate them into addition. In the quotient rule, think about what we've done before with exponential functions. B to the x over b to the y. If I see division, then I'm using subtraction for my exponents. So in my log, if I see division of my argument, I'm going to take the log of the numerator and subtract the log of anything in the denominator. Okay, the last rule is the power rule. So if I see something with an exponent and then there's an outside exponent, if I had these as numbers and asked you what would they do, we know that they would multiply. So if we see a log and its argument has an exponent on it, we can move that exponent down and multiply it times the log. So it would be y times the log of x. So here your exponents multiply. Here, same thing, my exponents are multiplying because this log represents an exponent. Okay, so we're going to try to put these, it's going to make a little more sense once we put some numbers with it as well. There's two ways we could do this. The first way, notice all these problems start with one single logarithm. So we're going to use the properties of logarithms to rewrite each expression in expanded form. Keyword here is expanded. When you expand, my recommendation is that you expand by starting with division and multiplication first. So how are you going to know? Well, you're going to look inside your argument and see if there's any division. No, there's no fraction. There is multiplication though. This is 6 that's multiplying by x to the 5th. So I can separate this into two logs. They're going to have the same base, and I do have to write what that base is. So this is log base 4 of 6. I can separate it from log base 4 of x to the 5th. And when I do that, we're using the product rule. So when that argument is multiplying, we're separating the log into two separate logarithms that are adding. Okay, now I'm going to look inside each argument. I don't see any other multiplication, but I do see an exponent. So that 5, we can bring to the front and use our power rule to rewrite that as the log base 4 of 6 plus 5 times log base 4 of x. So when you're trying to decide if you're done, you want to look inside each argument and only see a single term, a single number or variable, no exponents left. And then I want to also double check right here. This is log base 4 of 6. And I want to make sure none of these properties up here could be used. Like I want to make sure the base and argument aren't the same. Or if it was something like log base 4 of 16, something that I know makes a nice number, I could simplify that. But that's not the case here. So this is as far as I can expand my expression. Okay, let's try another one. So on B, it says the log base 7 of 3y to the 4th over x cubed. So when I see division, I start with that and separate it into two logs that are subtracting right away. Please don't forget to write your base. So log base 7 of 3y to the 4th minus log base 7 of x cubed. And now I'm going to look inside each parentheses and look for multiplication or division before I do anything with the exponents. This first one still has a multiplication of 3 times y to the 4th. So I'm going to need to separate this into 3 logarithms. Log base 7 of 3 plus log base 7 of y to the 4th minus the log base 7 of x cubed. So I can read this in expanded form and see, oh, these two were multiplying and they were being divided by this final term. And now I can take my exponents and rewrite them multiplying by the log instead. So I have first one staying the same, log base 7 of 3 plus 4 times the log base 7 of y minus 3 times log base 7 of x. And that's it. I should have maybe done it more step by step at the end there, but each argument has a single number, a single variable, a single variable. None of them had exponents on them still. So as you do more of these, you may not need to show like every single little step. Maybe you can jump from here down to the end once you realize these exponents are going to become coefficients. Maybe you can glance at the next one and see, ooh, there's a 3, an x, and a y. This is probably going to be 3 separate logs. These rules still apply with any base. So natural log follows the exact same properties. I'm going to switch colors and work it down here. So right away, I'm going to go ahead and say this is 3 separate natural logs. 3 times the natural log of x and the natural log of y cubed. I'm separating them all with addition. And then I'm going to take my exponent and use my power property, or power rule up from above. Natural log of 3 plus the natural log of x plus 3 times the natural log of y. And there we go. Notice we don't want to put the 3 at the front at the beginning. If each of these had a 3 in the front, I would assume that every single argument was cubed when really only the y was cubed. Okay, also these are 3 examples of expanding. A lot of times when we get to solving later in this unit, we're going to need to condense. Condense means we're going to go the other way to simplify or combine them. So number 2 says use the properties of logarithms to rewrite each logarithmic expression as a single logarithm. So I'm going to go ahead, that keyword single logarithm, this could be called, I guess, simplify, but also condensing. That verb gets used as well. So here I would start with changing coefficients. It's kind of going to be backwards order of what we just did on the front. Coefficients into exponents. And then decide how to combine them together. Okay, so let's try one. The first one says log base 2 of 10 plus 3 times log base 2 of x. I'm going to go ahead right now. I know that that 3 means my second log. I could write the x as being cubed. So log base 2 of 10 plus log base 2 of x cubed. And then if I see 2 logs being added in my answer, I write it as a single logarithm, so the base is 2. And in the argument, I take 10 and x cubed and multiply them together, and that's it. It's a single logarithm, and we used both the power property and our product property as well. Ooh, the next one only has numbers, but that's okay. It looks like no base is typed, so I know that's a common log with a base of 10. Still, same process. I'm going to go ahead and start with exponents on both here. So I have the log of 12 to the 4th power minus the log of 2 to the 4th power. And you can use parentheses again if it helps you keep everything separate. So I'm going to go to my calculator and actually figure this out. I'm going to type the log, well, I'm not going to type the whole thing, excuse me. I'm just going to type 12 to the 4th power. And when I do that really quick, I don't think I need to pull up my graphing calculator for that. You can type that. But when I do that, I get, oops, there we go, 20,736 minus the log of 2 to the 4th, which is 16. So when I combine them, they're going to divide. And then we can actually do that. Let's see if that turns out nicely. 20,736 divided by 16. And so in my final answer as one log, I have the log of 1,296. So log is still in the problem. I never actually typed log into the calculator. I only used the calculator to figure out what these numbers were to the 4th power and what I got when I divided by 16. Okay, y'all, let's do another condensing problem and then keep on going with a few more examples. So number 3, or part C, says 3 times the natural log of 3 minus the natural log of x. You have some choices here. It also, sorry, let me finish reading it, plus natural log of x minus natural log of 9. So you have a couple of choices. We could distribute this 3 and then go ahead and combine them. We could combine them first and the 3 would distribute to the whole expression. I'm just going to go ahead and distribute, oops. So 3 times the natural log of 3 minus 3 times the natural log of x. And again, you won't have to put those parentheses right now, but then we're adding it to the natural log of x minus the natural log of 9. So if I look here in the first half, I'm going to make these 3's into exponents. So you could have done this, in one step. So I have 3 cubed minus the natural log of x cubed plus, and then I can see these parentheses here are important. They want me to show that as these combine, this natural log is x being divided by 9. In the first half, I'm going to go ahead and bring it on over here. The left part of the problem, I can combine these two natural logs. 3 cubed, 3 times 3 times 3 is 27 over x cubed. So I just took these two natural logs, combined them using the subtraction to rewrite it as division. It's adding with the natural log of x over 9. And now two logs that have addition, I can combine them by multiplying their arguments. So that's the natural log of 27x over a 9 times an x cubed, which I am allowed to then reduce that argument. So it'd be the natural log, 27 divided by 9 is 3. And when I simplify my x's, there are more on the bottom. X squared will be left in the denominator. So you could do it that way. We could have, there's multiple ways. We could have combined these and do a fraction first, 3 over x, and then cubed that, but it was kind of purposefully telling you we need to combine these two, and then multiply our result together. All right, y'all, one other application, I guess, different way you could be asked this. It says, suppose that the log base a of 5 is p, log base a of 3 is q, and please fix this last one. Log base a of 2 equals r. Write an algebraic expression for each logarithmic expression. Okay, so turn this log into something algebraic. Okay, so let's see what it's saying here. Log base a of 50. Okay, well, it wants us to think about how we could, using only 5 and 3 and 2, and our operations of multiplication or exponents or division, how could we rewrite 50 using only these? One option, we could think of this as 5 times 10. So if I wanted it to be 5 times 10, I could separate it into the log base a of 5 plus the log base a of 10, and then I'd have to keep going. 10 wasn't in this list, but I can break it down again with a 5 times 2. So I can now separate this into the log base a of 5 plus another one plus a log base a of 2, since 5 times 5 times 2 is 50. Now that I have this expanded, I can replace it with the variables it gave me. Log base a of 5, we don't know what number that equals, but we know it equals p. So this is p plus another one, and log base a of 2 is r. So the algebraic expression I would get in simplest terms is 2p plus r after combining like terms. So that's what this section is asking you to do. Use your log properties to go ahead and replace the logs with some of these given variables. We should end with an algebraic expression consisting of variables, constants, and operations. Okay, the next one says log base a of 0.3. Well, I'm going to read this as log base a of 3/10, and I think that's going to help. If I write it as the log base a of 3/10, then I can see that I'm going to have the log base a of 3, which was given, and I can separate them with subtraction. Now, the tricky thing we haven't talked about yet is if this is subtracting 10, as I expand that out, I have to be subtracting both the log base a of 5 and the log base a of 2. So there's two ways we can write it. I could use parentheses and say that 10 is 5 times 2. So that would have a plus right here. But the parentheses would mean this minus would distribute to both of these. So it's also equivalent to writing it as, and I know I'm just maybe being a little too exact right now, but it's equivalent to writing it as log base a of 3 minus log base a of 5 plus log base a, minus, I've gotten on a roll thinking of a hard example I want to make up at the end here. Minus log base a of 2. So everything that has a minus sign would be going on the denominator and combining together by here multiplying, which I know feels weird. But again, this is another way that I could write it instead. Now let's go replace all these letters, or replace all these logs with letters. So log base a of 3 was q minus p minus r. And I'm just using, again, the given information up here. Okay, there we go. Okay, our last one, and then I do want to make up maybe a more exciting one. It says log base A of 1/27th. So when I see a fraction, first thing I'm going to do, separate the numerator from the denominator with subtraction. Okay, log base A of 1 was not given to us. But if you think back to the beginning of the lesson, log of 1, right? Any base to the 0 power is 1. So this is going to become 0 minus, and then we have to think of how to write this 27. So we could think of 27 as 3 to the 3rd power. That came up earlier in the lesson. I'll do this one a couple different ways. Then I could say, ooh, that's an exponent of 3 I can bring to the front. So this 0 won't matter here. I'll have negative 3 times the log base A of 3. And log base A of 3, this problem told me, is Q. So if I choose to do it this way, I get negative 3Q. Now, you might not have been thinking that. Maybe you were thinking to yourself, oh, I wanted this to be the log base A of 1, and then I wanted to split 27 into 3 times 3 times 3. Well, that's fine. It's a little more work. But I could have said 3 and 3 and 3. And those are all Q plus Q plus Q. And we were subtracting all of them. And log base A of 1 is still 0. So this is still going to be negative 3Q. Or you might have said to yourself, wait a second. 1/27th, that's the same thing as 3 to the negative power, because it flips, specifically 3 to the negative 3rd power. And I don't know if many of you would have thought this way or not, but that negative 3 would come to the front. Negative 3 times the log base A of 3, which I know this part is Q, so negative 3Q. So as long as you're using the properties properly, like in a way that's allowed, you're going to get the same answer. Okay, let me think of one really quick that I want us to maybe go ahead and, what have we been doing back here? Yeah, let's go ahead and condense. Okay, one more, because I felt like these notes were kind of lacking and some with some difficulty. So give me just a second here as we make this up. Let's go ahead and do a natural log. I'm going to make this 1/4 the natural log of x minus 2 natural logs of y minus 1/2 the natural log of z plus the natural log of e. Okay, so we have 4 parts here, and I wanted to put some in there with a fractional coefficient, so we can review fractional exponents. We said when we condense, the first thing we want to do is take those coefficients and put them as our exponents. Now, I would not, I don't know, as I write it, I don't typically write it as a negative exponent, these ones that have a minus. So I would probably do x to the 1/4 minus the natural log of y squared minus the natural log of z to the 1/2. Okay, natural log of e, well, think about what we know about natural log. It's the same base. When the base and argument are the same, this leaves a 1. Okay, great. Next part here, think about our last unit. We know that fractional exponents are the same as radicals, right? So it's our power over our root. So I could rewrite this as the natural log of x under the fourth root minus the natural log of y squared minus the natural log of the square root, oops, not of x, of z. And the plus 1 is still there. Okay, now the natural log of the fourth root of x, I know that it's going to actually be divided by both of these. So if you want to make it one fraction and put them both in the denominator right now, you can. I'll show you if we do it in 2 steps. Sorry, we're taking the natural log of this whole expression. We're going to get the same thing. So now I'm dividing again by the square root of z. I don't want a triple stacked fraction. If you're going to be dividing by the square root of z, it's the same thing as multiplying by 1 over the square root of z. So it would be in the denominator. And then the plus 1 is outside of the argument, but there's no way that I can actually simplify that right now. Okay, so looking at this answer, this is as condensed as I can get it. And again, the trick here is anything that has a subtraction, even if these weren't next to each other in the equation, we're going to be dividing by both of them. So it's going to take a little bit of practice, and then we're going to be actually putting it into practice even more when we get to our solving over the next couple of class periods. Please let me or your teacher know if you have any questions.